Hello, everyone. It's great to be here. Thank you very much for the kind invitation. So, as announced, I will talk about quantum reference frame transformations. We heard in the morning about that. We heard about the fact that it is widely expected that studying quantum reference frames and reference frame transformations could tell us something about the operational interplay between quantum theory and general relativity, as well as about processes with indefinite causal order. And for me personally, one of the big motivations for looking into this subject comes from this. But today I will not talk about indefinite causal order or time or gravity, as I believe that in order to make consistent progress, one needs to first set up properly a framework of quantum reference frame transformations. This is going to be based on a work with Esteban Castro, as you can see. And as you have heard, the subject of quantum reference transformations is all about perspectives. The different perspectives by different researchers working on the subject. And there is a significant overlap between them, but they are not all equivalent. Maybe some are better than others. And I'll try to convince you that to have a good reference frame perspective, you need essentially two main things. One is a good reference frame, and the other is a complete perspective, which requires that you introduce in your perspective degrees of freedom that we call the extra particle. How do I change that? Yes. So this subject is about understanding how physics looks relative to reference frames and how to transform between the descriptions relative to different such frames. And by now there is a huge body of literature on the subject, which I'm here mentioning just an excerpt, starting from the seminal work by Aharonov and co-workers, and then more recent years enforced by quantum information tools. This has been renewed interest, and then specifically the question about quantum reference frame transformations, which was kind of reinitiated and attracted huge interest by the work of Flaminia, Esteban, and Časlav. And then there has been all kinds of developments following that. And I will motivate our work by starting with this very simple problem. We've seen already very similar pictures today. So imagine that you're describing a standard, say, quantum particle by means of a wave function. And of course, this wave function is, provides some amplitudes for different positions of the particle, and these positions are implicitly measured relative to some reference frame. The reference frame A that is depicted here. And we know that if you have another such reference frame, here classical, there is a simple way to transform between the different descriptions, which is just given by a unitary transformation, which is a displacement or a translation in space that provides you with the new, with the description in the perspective of B, given, if you start with the description in the perspective of A. And now the natural question you may ask is what happens if this reference frame A is put in a superposition? How would it see the quantum state of the system S, for instance? And you can immediately see that there is a problem if you try to do that, because basically the system S would be correlated with the reference frame B once you move into the whatever that would mean, the position of or the perspective of this reference frame. That's intuitive, because if you just consider the position variable, and someone could make a measurement in the position basis of this new superposed reference frame, they should find consistently the previous reference frame transformations. Therefore, we may expect that the reference frame B and the reference frame and the system S would be correlated. Okay, so it means that we cannot actually have a pure state description of the system. So S should be somehow, because that's what I just said, it should be correlated with B. So there can be no such pure state description, and it appears that as we jump between the reference frames, some kind of information gets lost, which is disturbing because we expect that reference frame changes should be reversible. But then you would think, okay, maybe the problem is that we just did not include the original reference frame in our description. What if maybe this will be resolved if we include R and R prime, the different reference frames, in this case they were A and B, in each other's descriptions. And this is actually the proposal by Flaminia, Esteban, and Chaslov, which here I've written the transformation that they propose for switching between reference frame, which essentially proposes that in order to resolve this issue, one should consider the reference frame for which you start. And the proposal is that once we do that, we should get back to reversible transformations. And this has been developed in subsequent works in the so-called perspective neutral framework and so forth. But if you think about it, there is also a problem with that, because there could have been another system C over there. And by the same token as before, when I use the reference frame as a reference, I should see that C is also correlated with B and S. And therefore, how could I recover this pure state? Where did it go? This information that I initially had in my pure state description, again, I seem to get some irreversible transformations. And some people say, well, maybe you just need to include all the relevant systems. And this, naturally, I should say, this is another version of, let's say, the paradox of the third particle. It's essentially the same. This has been discussed in the important paper by Angelo et al. And I'm just presenting in some simpler version without any details, just giving intuition about the types of correlations we expect, and the fact that just by considering these correlations, we seem to arrive to a puzzle, that there will be some information being lost. And so, okay, one possibility is that we must just include all the relevant systems in this description, but this naturally brings me to the question, should we really include every single particle in the universe in our description in order to obtain reversible quantum reference frame transformations? I think this is somehow contrary to any spirit of locality of physical theories that we know. But it maybe it's just like that, because, in gauge theories, there are certain non-local degrees of freedom and so forth, so maybe this is okay. But somehow, even from a practical perspective, you might wonder whether such a solution is, what does it even provide us? Is it a real solution? Is this a testable prediction? What if I forget to account for single particles in a distant galaxy when I make a calculation and I conclude that some state should be pure when in fact it would be mixed? Is it useful to even have this type of reversible transformations when we only consider them in the idealized limit of a full universe or something like that? I think it's reasonable to desire that a theory of reference frame transformations would respect the following principle, that basically a transformation law relating the description of a system relative to two frames should just depend on the system and the two frames of interest. This happens to be the case for classical reference frame transformations, so it seems natural to desire this. And if we believe that such a thing would be possible, then it suggests that we should be able to derive, not guess, how reference transformations behave. We should be able to derive it because we could imagine that we describe, let's say, two reference frames as a system relative to yet another reference frame. And if the relations between the two reference frames of interest and the system are, like postulated, depend only on those reference frames and the system, they should not care about my reference frame in which I choose to describe them, but it may be helpful that I introduce it for the sake of deriving what these relations will be like. And this is basically the program that we took. And in the rest of this talk, I would like to explain to you the framework that we developed following this approach. So before I start, I want to make some things a little bit more precise. Like when we speak about reference frames for what? So we're talking about reference frames for degrees of freedom that correspond to unitary representations of groups. So this is one of the main assumptions. So we talk about certain degrees of freedom in our quantum description of systems that could be transformed by the action of certain groups. We also assume that the groups, when you are in the perspective of a certain frame and you look at the physics of interest, the Hilbert space you would associate decomposes into factors such that the group acts transversally over these factors, which means that each of these subsystems undergoes, has a well-defined action of the group on it. In addition, we'll be interested in ideal reference frames. And so here, the assumption is that from the perspective of an ideal frame, whatever that is, another ideal frame would be one of those systems that you see here, and it transforms under the left regular representation of the group. What this means is that it has a Hilbert space that has an orthonormal basis in one-to-one correspondence with the group elements, such that when you act with an element of the group on one of these, you get to the other, to another vector. And the idea behind this is that in this approach, a reference frame, a quantum reference frame, is seen as an extension, a generalization of the notion of a classical frame. So in particular, it should behave like a classical frame within any desired precision. Of course, the G may be not physical states, but just vectors, but we might approximate them. So we will like a quantum reference frame to behave in particular as a classical reference frame, but it might exist in superpositions. And then, now remember, we start our description always relative to some reference frame. Everything we talk about is, of course, expressed relative to some reference frame, whether this is explicit or implicit. So let us imagine now a system S and a reference frame A that are described relative to another reference frame E. And then I'm going to explicitly keep this reference here in the notation, saying to remind us that now we're discussing a description that's relative to some reference frame. Now, imagine now that another observer uses the reference frame A to describe S. Okay. They would use in general some other Hilbert space. But in my Hilbert space relative to E, I would like to describe the types of degrees of freedom that this other person is talking about. So a natural question then is, how does this using of a reference frame look like in the perspective of E? And in particular, we describe systems by means of measurements, transformations, and operators. So you may ask, what would be then an operator that, in the perspective of E, someone associates with the system S? So this is denoted by S relative to E. What would it look like when I represent it in the Hilbert space relative to E? And the answer is given by this expression. This is a well-established, well-accepted formula that one can find, for instance, discussed in this Bartlett-Rudolph-Speckens review paper on reference frames. And essentially, you can see these operators, they form an algebra which is isomorphic to the algebra of a system S, as it will be seen from the reference frame of A. And this is how I will denote it. I will denote this algebra by this simple S relative to A, but I'll keep here, the reminder that we have just described this algebra that the other person observes in our Hilbert space, which was relative to E. That is why I will keep this notation. I will keep it only for a while until I establish the fact that everything is consistent. So one can actually derive this formula. You can derive it by showing it is in fact the only algebra that operationally reproduces the non-classical reference frame transformations when you choose the system A to be one of the classical states G. So for this, we have an established theory. I will not question at all how we transform between classical reference frames. And one can show that this is the only isomorphic subalgebra to the one we hope to get, which operationally reproduces what we expect. So this is a good, faithful representation of the description of relative to Alice's frame in the Hilbert space of Eve. Now, I will take some time to explain some things that I personally enjoy very much thinking about, because I like how this all comes together very consistently. So, for instance, you may ask, we often speak about losing a reference frame, or how we should describe a system if we don't have a reference frame. Now, I described a reference frame A and a system S, but I, of course, used a reference frame E in the background in order to do that. And you may ask, but already within this picture, we can start describing what happens if a person who was using A loses access to A. Now, remember, the algebra that they were talking about when they were describing the system is this delocalized algebra here, which kind of has an overlap with the system S and the reference frame A, as I see them. So if they lose A, they will not be any more able to measure these operators in general, so that makes no sense to them. But still, there is a subalgebra of this algebra that I wrote that still will be accessible to them, because it is localized entirely on the system, from my perspective. But I'm asking also the question, what if they lose A, which is defined from my perspective? And so this subalgebra of the algebra I talked about is actually the algebra of operators on the system S, as I describe it, which is invariant under the action of the group. So in that sense, if a person loses access to the reference frame, they can still make sense of this subalgebra, and by assumption, because such a person only measures the system S by means of access to this reference frame in principle. So this is this algebra is what defines the system for such a person. There are also other implicit reference frames that for other degrees of freedom that such a person would use, but in particular for these degrees of freedom, they were using A, and if they lose it, they can still, by the exact same operational means, have access to the invariant algebra. But again, this invariant algebra is invariant of S given E. It was all defined in my perspective. So now you may ask, does it make sense to talk about the invariant algebra of a system or the relative system S as seen relative to someone without actually referring to an external frame E? And the answer is yes, and this is given by the following theorem. Basically, if you consider a system, an arbitrary system, Q, described relative to a reference frame E, then for any other reference frame that you can imagine, E prime, again, described relative to E, if you calculate this invariant algebra seen relative to E prime and expressed in my own space, then that is going to coincide with this algebra. And this is the same for every other reference frame that you can imagine. And this means that it doesn't matter which reference frame one uses. The description that they would have about this invariant, please, one has, and which reference frames you start from and which reference frame you lose. In any case, you would end up describing the same degrees of freedom, so it is all physically equivalent. So because of that, we can talk about the invariant subsystem of S, which I will hereafter call just the invariant subsystem, without any reference for external frame. And in a similar way, we can talk about the S relative to A, which hereafter will be called the relative subsystem. Again, independently of any reference frame, since S relative to A is part of the following invariant subsystem. If you take A and S together and express them relative to any E, then S given A is part of that. So it is well defined and independent of reference frames. So a few more technical points I want to make here is about the representation of these invariant algebras now. For compact groups, at least this thing holds strictly, and then we know that for other groups also, like the Galilei, which will be discussed, we can make similar statements. I'm not sure exactly which is the most general type of condition for which this holds, but in principle, let's say, for simplicity, we'll just imagine that we're talking about compact groups at the moment. The Hilbert space, if you have there is a unitary group action on this Hilbert space, this induces some decomposition of this Hilbert space of the following kinds. You have some into subspaces, and in each subspace you have these left and right factors, such that the group, when you express it with respect to this decomposition, these unitary operators, they look like this. There are irreducible representations in the left factors, and they act trivially on the right factors. So these are multiplicities of the reps. And so the invariance of algebra is actually all these operators that are left invariant under the action of the group. So it really has this type of form. With respect to this decomposition, it has non-trivial operators in these right pieces and identity operators in the left. And the invariant algebra actually can be obtained. There is a standard procedure of obtaining it from the full algebra on the full Hilbert space by just applying the so-called G-twirl super operator, or CPTP map, which is a projector that takes a given operator on the full Hilbert space and projects it down to this form. Essentially, it kills off diagonal terms, makes a depolarizing channel in the left factors. And this is a very, very, very convenient technical tool. Of course, if there is no external reference frame, you may notice that these pieces here in general would not make a lot of sense, because if there is no reference frame whatsoever, it doesn't even make sense to introduce those. And they could be traced out, but for convenience, I'm going to keep them here. You can think it's a little bit like a certain type of gauge fixing, because it makes all these calculations much simpler, because we're going to work with the same dimensions. And now, in the special, when we discuss the Hilbert space of the reference frame alone, like I said, it's by assumption transforms under the regular representation. So there is a similar decomposition where basically which runs here now over all possible irreps. For an arbitrary system, you can have different types of irreps, but specifically for the regular representation here, the sum is over all possible irreps. And here, these multiplicity factors are basically of the same, they're just copies of the irreps of the same dimension, if this is finite dimensional. So this will be used very shortly. So the thing is, now let us try to define what we mean by the perspective relative to A, or A's perspective for short. Remember, starting from the external reference frame, we have this description of the system and the reference frame. So I will suppress this reminder from now on for brevity. And then in A's perspective, we'll be describing essentially, there will be a Hilbert space in which the factor that we call S relative to A is natural, right? Because that is what we want to use the reference frame to describe. But then this Hilbert space will then be, so this is going to be isomorphic to this factor, which is the relative subsystem. And then there will be the complement, which is here just denoted by C. And I'm going to use this notation for the whole, for this Hilbert space, which carries Alice's perspective. Okay. Now, we can furthermore say something about the structure of this C, of this remainder. And this is this main theorem. So basically, if you look at this Hilbert space, which captures Alice's perspective, this factor, HC, decomposes like this. Just like a kind of isomorphic decomposition to the decomposition I mentioned for the regular representation. So we have exactly the same type of form. And actually, if you consider how the group acts on the joint system A plus S, when you represent it with respect to this decomposition, you will find out that the group acts like it gets localized on these left factors. It acts irreducibly on the left factors. So it's very much as if the way the group acts on a regular representation, but now it's kind of in a different decomposition, which is isomorphic to that. You still find the group to act on this piece, which is the complement of the system, as it is seen relative to A. You find that the group gets localized there and acts just as if it would act on the regular representation, no matter how it was actually acting on the system S. That is quite remarkable. So in that sense, we can say that if you look at the joint space, this is the gauge degrees of freedom, where the group acts irreducibly, and these are the invariant ones. Now, this is just to say that the relation between this decomposition, which is the standard partition, and this decomposition, which defines Alice's perspective, is given by this transformation, which we have seen earlier, I think. This has been also appeared in this paper by the name of disentangler. So it's been discussed in various forms, like in the paper by Flamini et al., in a certain form. So yeah, this is basically the relation. So now here I want to emphasize this idea that the perspectives of different reference frames have to do with these subsystem structures. So basically, given what I said, again, before, if you take the action of the group on the joint system and you transform it by this transformation, you localize everything on this piece here. So this is the gauge subsystem. We have this decomposition. Here is the gauge subsystem. Here is the system relative to A. And then there is this thing, this additional thing that remained from before, which is an invariant factors that are they're related to the invariant pieces that are inside the reference frame. And this we call the extra particle, because later when I discuss the Galilei group, it turns out that this thing could be interpreted as a particle. But in general, it's something else. But it just remained with us, this name, extra particle. So these are the degrees of freedom that are accessible to Alice. This is gauge for her because she doesn't have access to the external frame. But this is the thing. So it's not just the system relative to her reference frame that is included in these degrees of freedom, but there is this additional piece. And I want to convince you that this piece is essential for resolving the puzzle I said at the beginning. One important thing to point out is that when the reference frame is one of these definite classical states, G, one can show that these things here are in the maximally mixed state. In other words, well, you can argue this is one reason why this piece of information is normally not included in our description of physical systems. We usually just talk about the system as it is relative to a frame. But if your reference frame is in a quantum state, this may not be in the maximally mixed state. And I think it's very interesting because it shows that in principle, despite various attempts to achieve this in the literature, including by us unsuccessfully, it is not possible to put the quantum reference frame at the origin just by means of a gauge transformation. Because really there is this invariant information that you cannot change by means of the gauge group, which is contained in this piece, and it may not be in the maximally mixed state. That would mean that you are not in a classical state. So there is, in some sense, some objectivity about whether you are in a classical or non-classical state. Now consider two reference frames with this understanding. Now the degrees of freedom accessible by Alex and Beatrix are again given by the same, they are the same degrees of freedom. It's just the invariant subsystem. Because what we assume now is that they don't have access to to the external reference frame if. In Alice's perspective, this invariant algebra decomposes like this. There is the system, there is Beatrix's reference frame relative to A, and then there is the corresponding piece that we call this extra particle, this algebra. And in Beatrix's perspective is analogous, and this is the corresponding extra particle for Beatrix. And because we are describing the exact same algebra in just two different decompositions, you can expect that there should be a unitary transformation that relates the two. And one can find this by means that have been used previously in the context of the perspective neutral approach. You can just pass on from the perspective of Alice to the standard partition relative to someone external and go to the other one. And you can actually calculate what that transformation will be, just relating in the internal degrees of freedom. And we have done that, and I will not bother you much with the details, but there are all these different pieces of the invariant subsystem that we can talk about, and we can say how they transform. Now, what one can find from these transformations is the following subsystem structure, and this provides some further understanding of how these different factors interplay with each other. So basically, here the orange one represents, let's say, Alice's decomposition of the invariant system, and this is Beatrix's decomposition. And when you see some pieces, these algebras, to be displayed as overlapping, it means that they really don't commute. But if they don't overlap, they commute. Like, for example, this the extra particle of Alice is separate from the system seen from Bob, etc. So that there are these interesting relations. And one important thing that I want to stress here is that if you look at this picture, you will understand that it is in general not possible, starting from the state of just the systems S and B relative to A, to deduce how S and A would look relative to B. You need to add the extra particles in order to be able to answer that, because these subsystems and these algebras, they don't contain the same information. They're just partial descriptions of the full invariant system, so you don't have enough information to even answer if I see S and B in this way, how is going to B see me and the system? You have not provided enough information in the definition of the question. Now, I just want to say how this relates to the proposals mentioned earlier, in particular to the purely internal approach proposed by Flamini et al. And the related perspective neutral approach. Essentially, one can recover the previously proposed transformations in cases in which the subsystems that are taken of interest belong to the zero charge sector. There is in these different Q charges that label the different irreducible representations of the group. There is the zero charge, in which case basically the extra particle is one-dimensional, and there you just basically go down to a subspace. I mean, often people motivate this. You can understand this subspace as a projector, defined by a projector. And in that case, one would recover. But in general, these charges, for instance, total momentum, in the case of the translation group, they are physical. So it is not justified, in my view, a priori to assume that for any subsystems of interest we would consider, we should describe them by means of this formalism, which only holds when the total momentum, for instance, is zero. You know, that might be, for instance, the case in some constraint of the universe, but then it would not be the case for subsystems of the universe in general. So this condition guarantees gauge invariance, but what I want to stress is that one should not confuse it with gauge invariance. It is not the same. It is stronger. And now I want to go to the example of the Galilei group, which we've developed in our paper. I find quite insightful, and this is where the name extra particle comes from. So the Galilei group we consider in just one dimension, and we even consider it without time translations, just at a given instant of time. So this means that it's just a group described by two parameters, which is one is translation. So when you apply translation, normally this is how you would describe it, by an amount A. P is the generator of translations. And then you have boosts, and which basically leave the position observable invariant, but then they kind of change the velocity by adding a certain amount to it. And we'll just consider kind of the kinematics at the fixed stationary instant of time. And in this case, basically, the representation of the Galilei group is just given by this type of operators. You know, you have the generator of translation, the generator of boost, which is just the mass of the system times x, the x operator. And what you can see is that when you mount, you know, they obviously form a group. This is a representation of the group, but this is a projective representation. And this is because the position and momentum operators, they don't commute. So in general, we pick up a phase here. So in order to apply our theory of, of the regular representation, we're going to consider the central extension of this group, which promotes this phase to a parameter of the group, to an element of the group, a parameter basically of the group. And this is essentially how the central extension of this group looks like. You just add this phase, and this is the transformation law. For all the systems of interest that have fixed masses, as usually the systems of interest in our experiments, you know that nothing really changes whether we consider this group or the other. But for the representation of the reference frame, there is a change, because now a reference frame should be able, in principle, to measure theta, this phase. So you can think differently about this, but formally, mathematically, this is what it would look like. As we will see, I mean, if you're bothered by this idea, basically here the sum is over the irreps, which are here labeled by something that can be interpreted as a mass. So it's really like you have a system where the mass is a dynamical variable, just like position and momentum. In fact, I mean, there is this decomposition of these G states, which are the group elements, where, you know, like, similarly to before, you have the left and the right pieces, and this is how you would write in general. On these factors is where the group acts when you transform the frame, and this is what such a thing looks like. Now, if you're really bothered by the fact that we're considering something that might be unphysical or at least not compatible with the known physics, it's okay, because you'll see that we can restrict ourselves to a given mass sector, and then we will have a very nice interpretation of the reference frame, and everything that we will derive with this formalism could be used to infer what will happen in a fixed mass sector. So there are these different ways of thinking. I find it very interesting here in relation to, it reminded me in the morning Chaslov's talk and the discussion of the dynamical mass a little bit. Maybe there is a potential link with that, I don't know. But in any case, I think it's an interesting theoretical possibility to investigate. But even if you think this is just a mathematical device, it's still a useful mathematical device, and we can infer nice physics when we restrict this to a given mass. Okay, so what happens in this case, if we restrict to a given mass, is that a reference frame essentially can be interpreted, as we have shown, as consisting of two particles. One serves as a reference for position of the system of interest, and the other, A2, serves as a reference for velocity. Okay? And basically, I mean, these left and right factors are not the two particles I mentioned, but there is a transformation that relates these two factors in a given mass sector into the two particles I'm mentioning here. So you can think that one possible realization of this abstract reference frame is actually using two particles, one as a reference for position, one is used as a reference for velocity. And basically, you know, there is the center of mass of this is gauge, if you just ask how the group acts on this reference frame. And then basically there is this relational particle, this is well known, is well understood, this the Galilei group on a system of n particles. So you have the center of mass, and then you have relational degrees of freedom, and here is just the relational degrees of freedom corresponds to effectively one particle. And this is intimately related to the extra particle. When you start describing systems, there is this transformation U of g hat that maps this relational particle onto what we would call the extra particle. Another, and I'm going to come back to the transformations later, but essentially this is the type of picture we're going to get. So when you use this type of reference frame, you describe a bunch of particles relative to your frame, and in addition you have this additional thing, which is more or less, it's isomorphic to a single particle, which is defined by these relational degrees of freedom. Another simple example is the translation group. I would not present anything more than say, in the case of, say, the translation group, the extra particle really is just a single classical variable, which is equivalent to the total momentum of the system. Okay, and one needs to take it into account, though, in order to get all these nice reversible transformations. So let's now come back to the original puzzle. Remember, we said we imagine that we have a reference frame in superposition. We move to the perspective of this reference frame. What are we going to see? The first thing to note is that if we, you can do this analysis both with the Galilei group and with the translation group, but the principles are the same, so you can choose to think whichever you like. There is, however, an extra particle here, be it a full particle or just half particle, which is just the momentum variable. In any case, if this is, say, well-localized reference frame, a classical reference frame, then the extra particle, the extra particle for these systems relative to B will be in a maximally mixed state, like I told you. Now, when you jump to A, then you are going to see S and B relative to A in a mixed state, okay? The full information about the initial pure state, you might say, could still be there, right, between S and B, but it is not. It could still be there because, remember, there was this mixed state of the extra particle, so maybe this mixedness just comes from there. But actually, it's more complicated than that. It doesn't come from there. You cannot find the information about psi in these two systems, S and B relative to A. However, of course, you can recover it if you include the extra particle, because this is needed to get the full invariant subsystem, and then you will find out that the state is purified on the extra particle. Now, but wait, remember that there was this paradox came because we were imagining more frames out there, or more systems that if we take them in our description, you could argue they should be correlated with the position variable that is here. which means that it's correlated to the position variable carried by the initial pure state. So how is it possible that the state I claim, the information about the pure state is localized somehow entirely between A, B, and S, according to my previous analysis? How could it also be correlated with C? Well, the answer is that C, relative to A, is not separate from the extra particle I defined earlier. The extra particle is always defined for a specific system that you describe. We described S and B relative to A, and the extra particle is separate from SB relative to A. It comes as a tensor product with that. However, if you start adding more systems like C, D, and so forth, they will all overlap with this previously defined extra particle. And so it is by means of that they are correlated. If you just look at that algebra corresponding to C relative to A, yes, it contains information about that degree of freedom, but that's now not a separate system from the extra particle. So that is pretty much the resolution. When you take this extra particle into account, you can form reversible transformations. So it is possible to formulate local theory of quantum reference frame transformations, and by local I mean satisfying this desideratum, that it just relates the system and reference frames of interest. Different quantum reference frame perspectives can be understood as different partitions of the invariant algebra. And we must enlarge the description of a system relative to a reference frame by including this extra particle to achieve that. And our proposal is that one should include standardly this extra particle in the description of physical systems when one is interested in the relational description of quantum systems. So thank you for your attention.
Okay, thank you, Ognyan, for the talk. Hello? Can you hear me? Are there any questions? Yes, I'm not sure this works. It doesn't. I'm sure it doesn't work. Hello? Okay.
Hi, thanks for the talk. I find it's very important, but it still escapes my full understanding. So maybe it's super basic questions. I would like to understand better the significance of this extra particle and maybe operational significance. And now you gave two examples of that. One with this Galilean group, extending the Galilean group. And so my question is, in a conventional approach from Giacomini et al., one can also use two reference frames, one for X and P. Would it be then different, or where this extra particle in this example is to be found? And the second is related to this, is also for the example that, if I understand it, if the charge is not zero, you should have this extra particle. Is it in your framework possible from inside having XX only one reference frame, or relative one reference frame, find that there is a non-zero charge? And if yes, how?
Yes. So basically, I'll start backwards, I guess, because yes, the charge is by definition accessible. Because the assumption here is I have a symmetry group, a gauge group, meaning I don't have access to a certain reference frame that is used to describe that. And that one can define by just in the same way I motivated at the beginning. You lose access to the frame. If someone was describing what you were doing from the point of view of their frame, you were using it by actually performing something like joint measurements on the system and that frame. Now, the moment you lose that, you're not able to do that anymore. You cannot, however, you were not doing just those joint measurements. There was a whole algebra, and part of it didn't really need the reference frame. That's the invariant part. And that invariant part, you would still access. So by assumption, first we start here. The assumption is that you don't have access to a specific type of reference frame. And then you can ask what are then the accessible degrees of freedom. And mathematically, you can prove that these are accessible. Now, you may ask me, and I'm not sure exactly about the answer to this question, how do I measure this and that in these different circumstances? For instance, but maybe I should direct you here to Esteban to explain this better. Like you can ask, how do I measure momentum when I have translation invariance, for instance? In a translation invariant system, momentum is a physical quantity. It's invariant under the action of translation. But how would you do it in practice? Well, I don't know precisely, but Esteban, for instance, has given me a nice proposal for a physical model of how we could do that. Maybe you can...
Don't remember.
It was with this infinitely long, some kind of infinitely long current, and I don't remember.
You have like an infinitely long piece of tape with some obstacles,
yes.
And then you drop like a coin that starts rolling, and then you see when the coin stops, and everything is kind of translation invariant, or the obstacles, or translation invariant modulo these obstacles, let's say, and then you see when it stops, and then you measure the momentum in that way. Yeah, maybe you can think of being a continuous set of obstacles.
But you see, if you think that, for instance, mass, and if you think that you want to say, yeah, but there should be no way to measure outside of this universe momentum, for example. Yes, that at some point to make sense, when you make this claim, you're saying, okay, but then now my symmetry group is larger. It's really the Galilei group now. And if it's the Galilei group, then there is a different charge. There is the mass. And then you can ask me, okay, but how do I measure mass? And so forth. And I think that in principle, at least conceptually and the theoretical level, that is all falls off naturally just from the assumptions of what degrees of freedom you don't have access to. So in that sense, one could cook up specific models, I think, but in general, what I find helpful is to imagine that there is one reference frame, just like I did here. Think about the system and someone losing reference frame, and you can still see that just because they lost that reference frame, there's nothing that prevents them, in principle, from accessing all these other degrees of freedom, which I assumed that they could access from the start. So it's in this language, at least, it's a very consistent point of view. And now to Flaminia's formulation and yours. So you're asking, what if we use two particles for reference frame? You could use two particles as a reference frame. Why not? But and that is essentially what we kind of do. But I do not know what you have in mind when you say that you would use it. In which specific transformations are you going to do? So I'm not 100%. Do you have a specific
maybe we can discuss this later. Yes, perhaps.
Yes.
I'm going to ask now if there's any questions online. Perhaps we don't have. Then are there any questions here? You.
Thanks for the really nice talk, Ognyan. It's a really naive and conceptual question because this is the first time I heard about the paradox of the ferroparticle. I was wondering if you know about this. There is this problem called the third-person problem that Rovelli talked about. It's related to his relational quantum mechanics interpretation. And to me, it feels like conceptually they are really close to each other. Do you have any intuition on that?
Actually, I'm not familiar with this problem, so I can't comment on that.
This is basically the Wigner-Friends paradox, where you have apparent paradox because from different perspectives you have different description of the same system, and you can get a paradox from a third-person point of view.
I don't know.
If you continue like this, you can have, like if you go to meta and meta and meta meta, you have an infinite regression, and so you need to describe the whole universe.
Just one comment I want to say is that this we are not doing friend situations in our analysis. So the way to think about it, I find this the cleanest and safest way to understand this conceptually, that it is consistent, is to think that you are always on one side of the Heisenberg cut. It's just there are different systems that might be used as reference frames. You may lose them, you can use them, you can switch between them, and all of that. Any potential measurement using these frames is always read out on our side of the Heisenberg cut. So we don't really put observers in that sense on the bad side of the Heisenberg cut, so to say.
But do you feel like there might be some kind of analogy between the two problems in a sense? Like, for example, it's not an observer here, but here it's a quantum reference frame, and you can get more or less the same type of paradox but in a different.
Potentially, yes, but I must really, I cannot tell you any insightful answer because I've not thought about. I'm not quite familiar with.
Let's thank Ognyan again, please.
Thank you.